Hello, my name is Chris Fisher. Thank you for your interest in our presentation titled Using Cognitive Agents to Design Dynamic Task Allocation Systems. Our central thesis is that cognitive models may have utility outside of scientific theory development and testing, such as supplementing certain types of artificial intelligence systems that deal with human behavior and cognition. We will focus on a type of artificial intelligence system that we call an autonomous manager. And an autonomous manager is a system that monitors the performance of multiple people in a team-based workflow and dynamically allocates tasks in order to improve performance. An autonomous manager may use a variety of methods to determine optimal task allocation, such as artificial intelligence, mathematical optimization, algorithms, and even cognitive models. In some work environments, team members have different skills and different work demands. Moreover, work demands may change across time, and members of a team may differ with respect to the sensitivity of performance to work demands. Taken together, this suggests that performance is non-stationary and could be improved through task reallocation. Assigning this responsibility to members of a team may not always be feasible, and monitoring the performance of oneself and others could lead to performance degradation on the primary task. In such cases, delegating task allocation decisions to an autonomous manager would be preferable. Cognitive models provide quantitative predictions about performance, making them a natural choice for inclusion in artificial intelligence systems that make decisions about human performance and human behavior. Moreover, cognitive models may provide insights into the reasons that performance changes across different situations. Another benefit of cognitive models is that they require less data compared to some types of artificial intelligence. Although neural networks, for example, are very flexible, they have very high data requirements. In many applications, collecting the required data may not be feasible. The use of a predefined structure, such as a cognitive model, can help to reduce data requirements. Cognitive models can be used in autonomous managers in at least two ways. First, cognitive models can be incorporated into the decision system of an autonomous manager in order to predict behavior and understand the performance implications of alternative task allocations. Second, cognitive models can be used as a simulated agent that performs the task. With this approach, it is possible to stress test the performance of an autonomous manager using a wide range of cognitive models with different performance characteristics. We will call the simulated agent a cognitive agent. The design space of autonomous managers is potentially quite large, including decisions about models of individual team members, performance metrics, optimization techniques, as well as other factors. Likewise, the range of behavior in a task can be quite extensive given individual differences. It is not feasible to explore large areas of this design space empirically. However, it is possible to explore large areas of the design space through the use of computer simulation and cognitive models. The results of these simulations can inform empirical investigations. In what follows, we will present a simulation study designed to illustrate the use of cognitive models in designing autonomous managers. In our simulation, we vary two factors. One, the cognitive model used in the decision system of the autonomous manager, and two, the type of cognitive agent that performs the task. In some cases, the cognitive model and the cognitive agents are matched. In other cases, they differ. We were particularly interested in evaluating the performance and robustness of autonomous managers. For example, some autonomous managers might have high performance when the cognitive model in the decision system matches the cognitive agent performing the task, but could be less robust across different cognitive agents. Given the high level of individual differences, the Robustness of an autonomous manager is an important criterion to consider. Before proceeding to the design of the simulation study, we will provide an overview of a novel task for dynamic task reallocation. We developed a novel variation of the multi-attribute task battery, or MATB, which was designed to study multitasking demands typical during piloting. Our novel task is adapted for the demands encountered in intelligence, surveillance, and reconnaissance, also called ISR. We call this the ISR MATB. The ISR MATB uses classical cognitive tasks to capture 4 important task demands in ISR: goal switching, information search, synthesis of information into actionable decisions, and task dependence. The ISR MATB captures these task demands with 4 subtasks, which we will describe in turn before explaining the interrelationships between the subtasks. We modified the psychomotor vigilance task, or PVT, to emulate demands for sustained attention and goal switching in ISR environments. After a delay of 0 to 10 seconds, a target appears on the screen, and the person assigned to this task must respond to the target within a deadline of 2 seconds. The target is one of 4 stimuli: a gray Q, a gray O, a black Q, or a black O. As I will explain later, the target can be used in other subtasks. If a response is not given to the target within the deadline, the target cannot be shared with those completing other subtasks, in which case guessing is the only possible response. One common task in ISR is to sift through video feed for relevant targets or assets. In many cases, the video quality is low and there are many distractors. We emulate these task demands with the classic conjunctive visual search task. In the conjunctive visual search task, the goal is to identify whether a target, such as a black Q, is present. The target is intermixed with an array of distractors which match on a single dimension, either the color or the shape. In this case, the distractors would be black O's and gray Q's. Another common task in ISR is monitoring communication channels and audio recordings for targets, embedded in noise and intermixed with many distractors. We emulate this task with an auditory search task in which participants scan up to 4 channels for the presence of a target. In ISR operations, it is common to synthesize information from multiple sources into an actionable decision, such as whether to deploy or withhold an unmanned vehicle. We use a multiple queue decision-making task to capture this aspect of ISR operations. As shown in the table, there are 2 queues: confidence, which is whether the intel is believed to be accurate, and target state, whether the target status is the same or different in the visual search and auditory search tasks. For example, the target state is the same if the target is present in both tasks. Importantly, all queues must be known in order to perform greater than chance. This means that the decision task depends on accurate performance in the other tasks. The diagram shows the interdependencies between the subtasks. After an interval of 0 to 10 seconds, the target is presented in the PVT. If acknowledged, information about the target is shared, allowing it to be used in the visual and auditory search tasks. The visual and auditory search tasks can be completed concurrently because they are independent of each other. However, the decision task cannot be completed accurately until the target state is ascertained in both the visual and auditory search tasks. After the decision is made, a new trial begins. The goal of the present simulation study was to examine the accuracy and robustness of different autonomous managers across a variety of cognitive agents. In total, there were 25 conditions formed by crossing 5 autonomous managers with 5 cognitive agents that completed the task. Each run of the simulation was 60 minutes in simulated time and consisted of 2 agents of the same type. After each block of 10 trials, the autonomous manager made a decision about task allocation based on the data observed so far in the simulation. Parameters for each agent were sampled from a probability distribution to introduce variability in performance. Each condition was repeated 500 times to approximate the long-run average performance. As shown in the figure, our goal was to develop a set of cognitive agents with a wide range of performance characteristics. The figure shows the relationship between workload, defined as the number of assigned tasks, and performance. The black line represents accuracy across time, and the red line represents workload across time. The accuracy scale is on the left-hand y-axis, and the workload level is on the right-hand y-axis. Please refer to the text for details. Our simulation consisted of 5 autonomous managers based on cognitive models ranging in complexity. Many of the cognitive models match the cognitive agents described on the previous slide. The constant autonomous manager assumes each agent has constant performance. The recent maximum autonomous manager uses the most recent block of data for each cognitive agent as the best estimate of performance. The limited capacity autonomous manager assumes that each agent is of a limited capacity type. This autonomous manager fits the model to all available data and uses the predictions to guide task allocation decisions. A similar process is used for the Yerkes-Dodson autonomous manager. Finally, we added a random autonomous manager as a basis for comparison. This autonomous manager randomly allocates subtasks to cognitive agents. We measured accuracy as a percentage of maximum possible for a given cognitive agent. The results are paneled by cognitive agent type, with the type listed in the title of each panel. Within each panel, each autonomous manager is color-coded according to the legend provided above the figure. We found 3 important findings. One important finding was that performance was the greatest when the autonomous manager's internal model matched the cognitive agent performing the task. A second important finding is that autonomous managers based on simpler models tended to be more robust when the cognitive agent did not match. Although the constant autonomous manager did not always achieve the highest accuracy, it was typically among the highest performing autonomous managers. A third important finding is that autonomous managers struggled to improve performance for the fatigue dynamic cognitive agent. Improving performance for this type of cognitive agent is challenging because its state is dynamic and changes as a function of previous task allocations. Our goal in this research was to use cognitive models to explore the design space of dynamic task allocation systems. One insight from our simulation study is that simple cognitive agents have the potential to be robust to variability in team performance. Robustness is important given that performance differs across individuals and even within the same individual. Taken together, our findings suggest that simple cognitive models should be considered in the design phase for autonomous managers. There are several potential avenues for future research. One avenue is exploring a larger set of cognitive models. A second avenue may examine whether simple cognitive models are more robust in alternative tasks. A third avenue is to find simple models that work for the fatigue dynamic cognitive agent. In related simulations, we found that the simple constant autonomous manager worked well for a dynamic ACT-R model of memory. These results suggest that the constant autonomous manager may work well for at least some types of dynamic behaviors, but other dynamic behaviors may require novel solutions. Thank you for your interest.